Hi, everybody. This is circular motion part two. We are going to go over centripetal force, then we'll do a couple of example problems having to do with centripetal acceleration and using those two equations that we got from the last video. So this is real quick. Recall the equation for centripetal acceleration. So we have two, remember. We have AC equals omega squared r, and that also equals v squared over r, right? Based on the relationship that velocity equals omega times the radius. So if we look at Newton's second law, F equals ma, right? And we want to make that centripetal acceleration, we can just substitute in, if we want to make that centripetal force, we will substitute in centripetal acceleration. So that would give us m omega squared r, or mv squared divided by r. Both of those will work for centripetal force. This is really more of just a demonstration. We don't talk a whole lot about centripetal force right now. It'll come up later, but this is where that comes from. All right, now for some example problems. Artificial gravity. As in the classic movie 2001: A Space Odyssey, if you haven't seen it, you gotta see it. A cylindrically shaped space station, 29 feet in radius, can be revolved to create artificial gravity. Calculate the spin rate needed to generate 1 g of acceleration. So let's look at our givens. We have acceleration equals 1 g, which is 9.81 meters per second squared. Now remember, 1 g is not inherently negative. Gravity is pulling down, and that's what makes that negative. But 1 g of acceleration is 9.81 meters per second squared. It doesn't always have to be negative. And then the other given we have, the radius is 29 feet, but we need that in meters. I can't remember feet to meters off the top of my head, so I always go to inches and centimeters. It takes us a couple steps, but it's not too slow. If you know the feet to meter conversion, then by all means use that instead. It cuts down on the time that you're using this conversion rate. And physics is all about saving time, especially when you're having to do this on a test. So we've got 29 times 12 times 2.54 divided by 100. So we've got 8.84 meters for our radius. Right? Now, what we'll do is we will solve for our omega. So we have, right, because it asks for the spin rate. Spin rate is omega. So we have centripetal acceleration. We have r. What we'll do is we'll plug that into the omega squared times r. Right? So omega would equal the square root of a divided by r, which will be the square root of 9.81 divided by 8.84. It's going to be very close to just the square root of 1. 9.81 divided by 8.84, 1.05. So you've got 1.05. What unit would we use? So what we did is we took meters per second squared, and we divided that by meters, right? So that canceled. So we got seconds to the -2, but we did square root that. So that gives us seconds to the -1st. And remember, when you get seconds to the -1st, you're really getting radians per second. So, but 1.05 radians per second it sounds like that's not very much. But if you remember that if you travel in a circle 360 degrees, that is 2 pi radians. So an entire revolution around a circle is about 6.28 radians. So we are, that's not just 1 degree per second, right? That is 1 radian per second, which is significant. That's a lot more than just 1 degree. Now, that also seems kind of slow, but we can actually find out just to prove that this is not some nonsense answer. We can look at what the velocity of that would be, right? So if we look at AC equals v squared over r, v would be the square root of a times r, which if we did that, we have square root of 9.81 times 8.84, 9.31 meters per second. 9.31 meters per second. And a meter per second is not something to mess with, right? Meter per second is actually pretty fast. If you can travel a full meter every second, you're going pretty quick. So 9.31 meters per second is about 21 miles per hour, right? So you are not just casually moving along. That is a pretty quick move. So 1.05 radians per second is not unreasonable. All right, then we have step 2, right? What would the artificial gravity, how would that change if Dave walks up the tunnel toward the center of the space station to try to disengage Hal? Hal is the computer that's running the space station in 2001: A Space Odyssey. So, spoiler alert, you got to turn the computer off. The computer goes crazy. But we want to change the radius, right? So let's look at this. If we have AC equals omega squared r, but that radius drops in a multiplication relationship, that should just directly change the other side as long as omega is constant, right? So let's think about that. If we have, let's say we form a human chain, right? And we want to start moving around the center person. Well, that actually makes a big difference when we are talking about how fast someone is moving, right? So if we have this person right here that's right next to the center, they don't have to move very much, right? But as you start getting further and further out, you actually have to move pretty quick. However, let's say that this circle is moving 1 revolution per minute, right? We're just walking in a circle 1 time every minute. That person in the yellow, they're not going to have to move very fast, right? But then that person on the green, they're going to have to walk a little bit faster. Blue is going to walk a little bit faster still. And then red is booking it to keep up with everybody, right? Because they have so much further to go. However, no matter where you are, and if you're that black, yellow, green, blue, or red dot, you're still going 1 revolution per minute, right? You're not going to go around that circle any faster as long as we hold that line still, right? That line needs to stay true. If it goes untrue, then everything gets messed up, right? But as long as we hold that line, omega should not change, right? But we have another equation to consider. If we look at AC is v squared divided by r, right? I'll actually put that down below. V squared divided by r. If you have something at the bottom of a fraction and that starts changing, that has an inverse relationship, right? So if radius decreases, that will cause acceleration to increase. If radius increases, that causes acceleration to decrease, right? It's an inverse relationship. So let's look at that. If we use the image that we had over here again, right, the bullseye over here, each person, as you get further and further out from yellow to green to blue to red, if we increase the radius, right, that person needs to go faster to make that full circumference, right, because they have further to go. But in this problem, we are decreasing radius. So if you decrease that radius, that will also decrease your velocity. So radius, if you decrease it, that wants acceleration to go up, right? In this relationship, if radius is in the numerator, no, I'm sorry, in the denominator, if it's in the bottom of that fraction, it wants acceleration to increase. However, your velocity is also wanting the acceleration to go down because it is in the top of the fraction. Now, let me just show you a quick example, right? if we have acceleration equals 2 divided by 4, right? That means that your acceleration is 1/2. Now, if we want to change that, right? Let's change the bottom of that fraction. Let's cut it in half, and we'll say that it goes from 4 to 2, right? Cut the radius in half with this relationship, cut the bottom number in half, and you essentially double the acceleration, right? It went from 1/2, now it's at 1. So whatever you do to the bottom, the inverse happens to the acceleration. So that's showing that radius, if you decrease it, it wants the acceleration to go up. And then obviously for the velocity, if you change the top of a fraction and make that go down, it should make the other side go down too. So if the velocity wants it to go up, the radius wants it to go down, which one's correct? Which one's going to win? Well, if we look here, velocity is squared, which means that the effect that the velocity is putting on the acceleration will most likely win out, and the acceleration will go down. Right? So that means, so the question is, will the artificial gravity change? So artificial gravity will decrease if you start moving towards the center, right? And then once you get to the center, as that space station is rotating around you, but you're at the center of the axis, you should feel weightless, right? If you are in true zero-G space. All right, next, David and Goliath. Talk about some sling physics. So, young David, who slew Goliath, experimented with sling physics before taking on the giant. He found that with a sling length of 0.6 meters, he could develop a speed of 8 revolutions per second in his weapon. Now, that speed is angular speed, don't forget. That's not meters per second. If he doubles the length of the sling, he can revolve it 4 revolutions per second. Which sling length requires the greater centripetal acceleration for number 1? So we've got two slings. Let's just call it sling A and sling B. So the radius of sling A is 0.6 meters, and omega for sling A is 8 revolutions per second. For sling B, we double the radius to 1.2 meters, and the omega gets cut down to 4 revolutions per second. So, which is going to require the greater centripetal acceleration? Well, we've got omega and r. We need acceleration. We have an equation for that. That would be omega squared r, right? So, we need acceleration. It's already solved for acceleration. So we can just plug things in. If we want acceleration for sling A, we take 8 squared times 0.6. Let's see, 64 times 0.6, we get 38.4. That would be in meters per second squared. And then for sling B, we have 4 squared times 1.2. So 16 times 1.2, 19.2 meters per second squared. If you'll notice, that is half, right? The acceleration is half for sling B as it is for sling A. So we can actually look at the relationship here. We have omega squared r. So let's see, let's say we've got omega A and RA. How did we change that for sling B? So what we did is we cut in half the omega. So we have 1/2 omega A. And then what did we do to the radius? We doubled it, right? 2 times RA. And that gives you, right, that would give you the acceleration for sling B. So you would think that 2 and that 1/2 cancel, right? But that's not true because that 1/2 is now squared. So that means we have 1/4 omega A times 2RA would give you the acceleration for B. 2 times a quarter is 1/2, right? So 1/2 of the, I guess, yeah, that's a confusing way to say it, but you would have 1/2 acceleration of A. 1/2 acceleration for sling A would be the acceleration for sling B, which holds true, right? That relationship works out. Now let's look at number 2. Which sling length releases a stone with a greater linear velocity? So let's look at linear velocity. We have the acceleration, centripetal acceleration is v squared over r, right? V squared over r. So we can look at, we also have v equals omega r. So both of these we can try, and we'll do the math both times to see which one's right. So let's look at the acceleration for sling A. I'll do this in red, keep things consistent. The acceleration for A is, oh wait, no. We need velocity. I'm so sorry. Velocity is the square root of A times R. This is for sling A. So we have the acceleration of A is 38.4 times the radius, 0.6. Square root it, you get 4.8 meters per second. Now let's try for sling B. Let's use the numbers for that. It's still A times R. So we would take the square root of the acceleration, 19.2, times the radius, 1.2. You also get 4.8 meters per second. Okay, that's weird. Let's go ahead and try the other one, shall we? Let's see if we get something similar. So we have the velocity, velocity of A. That would just be omega A times RA. So that would be omega A is 8 times 0.6. That is 4.8 meters per second. Not looking good, right? So velocity for B, we would take omega B times RB. That would be 4 is the omega times 1.2. What do you know? We've got 4.8. So it looks like consistently we're going to get the same answer, which means that the sling length is going to release a stone with the exact same linear velocity. Now, why would that make sense? So let's do this a similar analysis like we did up above. Let's take velocity of A equals omega A times RA. Now, if we went to look at the velocity for B, what did we change? So omega A gets cut in half, right? For omega B, goes from 8 to 4. For radius A, we doubled the sling length, right? It went from 0.6 to 1.2. So that would be 2 times radius A. What do you know? 1/2 and 2 cancel. BB should equal BA. Nothing changes. So that all works out. No matter which sling he uses out of these two options, he will get the exact same linear velocity. All right, so that is circular motion part 2. Next time we will go over what an acceleration vector looks like for a realistic uniform circular motion.